Today we are talking about angles of elevation and depression. Those words should ring many bells. You've seen this before. When did you see that? Jack?
Was it last year?
Nope.
Year before.
Geometry. Unit 8. When you learn trigonometry in geometry, the last thing we show you before that test is the angles of elevation and depression. In fact, we don't really go any further than what you learn in geometry. So everything we're about to do is pure 100% review. Some of you, in fact, may have learned this from me because you had me in geometry class. Now, how I teach specifically the angles of depression may differ from how your teacher taught it, so I'm just going to give you that fair warning. Otherwise, again, this should look exactly the same. Before we do a problem or two, we need to make sure we have some basic diagrams in mind. You're going to want to have these visuals in your head as you're setting up the problem. It'll make that process easier. So first we're going to do the angle of elevation. And I want you to understand that this is a perspective thing. So we're going to do this from a person's eyes. Angle of elevation, angle of depression, that's really looking up versus looking down. And we have to have a point in the middle where you're not doing either of those things. And that would be looking straight ahead. And I refer to this as neutral. From here, to make an angle of elevation, we're going to have to go up. That creates our angle. For these problems, we're only focused on a triangle and not a triangle on a plane. Just a triangle, period. In that case, we always refer to this angle as theta. We don't use alpha for this triangle when it's a standalone triangle. From here, you can clearly see the right triangle being formed. This is our angle of elevation diagram. Let's do one for angle of depression. I'm going to start my stick figure much higher since I'm going down this time. So again, we need to start with a neutral line where he's looking straight ahead. And this time, if we're creating an angle of depression, that means we're going to be looking downward. And again, you can see how the triangle is going to finish from there. This is our angle of depression. When we do an actual problem, you're going to want to draw the picture semi-realistically to make sure you place everything correctly. but then also have the correct diagram in your head so that it kind of guides your drawing in the correct direction. So you'll be thinking about these things simultaneously. If you don't set up the picture correctly, obviously you're more than likely going to get the wrong answer. So setup is extremely important here. First example, a ladder leaning against a house makes an angle of 60 degrees with the ground. The foot of the ladder is 7 feet from the foundation of the house. How long is the ladder? So first off, this is pretty much the only time where it won't directly say angle of elevation or angle of depression in the problem. Other times it blatantly states it. So this is one where you kind of have to draw the picture to figure out which diagram we're looking at here. And again, get as realistic as you'd like with this. It'll help. I just used some silly doodles. So we have a ladder leaning against a house. And I had to remind my sophomores in geometry that if you put a ladder against a house and you intend to climb it, it can't be vertical on the house. It has to be leaning against the house. Now I'm going to exaggerate that a bit here, but the idea is still the same. So there's our house, there's the ladder, we have the ground here. Let's go back and fill in some information. Ladder leaning against the house makes an angle of 60 degrees with the ground. The ladder makes an angle of 60 degrees with the ground. Ladder, ground, angle here, 60 degrees. So as you can see, we clearly have an angle of elevation happening here. Hopefully you can clearly see the right triangle. The foot of the ladder, so the base of the ladder, is 7 feet from the foundation of the house. We're talking about this horizontal distance here is 7. How long is the ladder? We're talking about the length of the physical ladder. So the ladder itself is what we're trying to find. This picture has a lot going on with it, so I'm going to redraw my triangle and just focus on the important information. Of course, this is optional, but sometimes when you have a crowded picture, it can be hard to focus. So we know that the bottom leg is 7. We know our angle in question is 60 degrees. And then we're trying to find the hypotenuse. Reminder, this is one of the many reasons we teach trig. If we had the other side here, we could just use Pythagorean theorem and then move on. We don't have that. This is enough information to use trig, use one of the 3 original functions. So we're going to label HOA. Hypotenuse is always across from the 90. O is opposite the angle that's given, and then A is the remaining side. We are given A, and we want to find H. Which function are we using here?
Cosine?
Yes. So I'm going to set up my equation. Cosine of theta is equal to A over H. And then we fill in our information. Cosine of our theta is 60 equals A is 7 over H, which we don't know, so we're just going to leave H. Reminder, when you have an equation and you have at least one of them being fractions, then a go-to method is to cross multiply. In this case, my cosine isn't a fraction yet, so I'm going to make it into a fraction. I'll put it over 1. And now I can do the butterfly method, just cross multiply those. Crossing on the left, I have h times cosine of 60, and I'm going to write exactly that, h, and I'm physically writing the times sign as a reminder of what to do next. Times cosine of 60 equals 7 times 1 is just 7. And this is where some students tend to overthink the problem. The goal is to solve for h. These are being multiplied, so I'm going to divide off that cosine on both sides. And then I'm just going to type that right side into my calculator. 7 divided by cosine of 60, and it actually is a really nice number if you've already done the math. Reminder, make sure your calculator is in degrees, it should be. 7 over cosine of 60. And it comes out to be just a nice 14. No need to round anything. And the units of this problem are feet, so I'm going to put feet on that. That's all there is to it. Questions on this first example? Example 2. From the top of a tower, the angle of depression, as you can see it clearly states this time, angle of depression, to a stake on the ground is 72 degrees. The stake is 26 feet from the base of the tower. How tall is the tower? So since I know it's an angle of depression, I've got this diagram on the right here in my head. That's kind of what I want my drawing to make its way towards. So just kind of think about that as I set this up. So in this picture, I have a tower, and then I have a stake on the ground some distance from it. And we're going from the top of the tower down to the ground, so just kind of imagining, I'm going to put my tower on the left side because that is going to go down to the ground from here. So we have our tower. And then just to create this visual, I'm just going to put a floating point here just to represent the top of the tower. And then a stake on the ground somewhere down here. So we're going from the top of the tower to the stake on the ground. And then to create that angle of depression, I need that neutral line. This is why it's important to have the diagram in your head as you're drawing, so that you don't accidentally draw your triangle like this, because that it clearly also looks like a triangle. It's a common mistake that's made. And then we can finish off the rest of the triangle and place our 90-degree angle. Let's fill in some info here. The angle of depression is 72 degrees. The angle of depression is this top angle up here. It's from the perspective of the top of the tower, looking down. The stake is 26 feet from the base of the tower. So the base of the tower to the stake, this distance is 26. So we're going to put that number on the horizontal of the triangle. Question is, how tall is the tower? So what we're trying to find is the vertical side of the triangle. Again, if it's helpful, you can redraw just the triangle once you have the setup correct. Just so we focus on the pertinent information. Do you have a question, or are you giving me an answer?
I have a question.
Go ahead.
Instead of moving all the numbers and the question mark over, why don't you just use the original triangle?
I'm saying this is an optional thing to do, because some people get kind of, I guess the best word to use is overstimulated by all the drawing.
If I do it like that, that'd be okay.
That's incorrect. That's what I don't want you to do. I can tell you more about that one-on-one, but just telling you right now, that is not right.
Okay.
Okay? So, let's label our HOA. H, hypotenuse across from the 90. O, opposite the given angle. A is the remaining side. For given A, we want to find O. Which function is that? Good? Tan. Good. Tangent. Tangent of theta equals O over A. Just set up the basic function, and we fill in the information. Tangent of 72. Give me just a moment. (72), there we go, equals O, which is unknown, so I'm going to leave that. And I don't want to mistake that for a 0, so I'm going to give him a little curl. You can also use X or something if you want to do that instead. O over my A is 26. And we need to solve. Again, when you have a fraction in one and not the other, we can still use cross multiplying. Just turn both of them into fractions. And we'll cross multiply here. We have 26 times tangent of 72 is equal to O times 1. That's just O. This time, O is already by itself, so we just need to enter this into our calculator and round to get our answer. So we have 26. The times is optional. The calculator will understand its multiplication if you don't put it in there. Just an FYI. Tangent of 72. And we'll round that off to a nice 80. And we're still in feet. 80 feet. So that's the ideal scenario because it's the least amount of work. It gives you the answer straight away. Questions on example 2? Okay. Last one. There is a point on the ground 50 feet from the base of a 66-foot tree. Find the angle of elevation. So again, we're directly told there's an angle of elevation here. We have a tree and we have a point on the ground. That's pretty much it. And again, I already know that my diagram is supposed to look like this. So I'm going to have the tree be the vertical, so it's going to be on the right side here. So we have our tree. And we have the point on the ground some feet away from it. Now the angle of elevation is going to come from the perspective of the point. So we have the horizontal, the neutral line, and the hypotenuse, creating that angle of elevation. And then we can finish off the triangle from there. We know that the point on the ground is 50 feet from the base of the tree, so that's the horizontal distance. 50 on the horizontal. The tree itself is 66 feet tall, so 66 on the vertical. This time we're looking for the angle itself, so I'm just going to put theta there, since we don't know it. Again, if you want to use the original triangle I drew, you can, or if you want to draw a separate one that just has the information, we can do that. That's what I'm going to do. So again, we don't know theta, so that's what we're looking for. We have 50 on the bottom and 66 on the vertical. HOA. Once again, we have O and A given to us. We could find H, but we don't. There'd be no reason to. We still need to find the angle regardless. So let's just use O and A, tangent. Tangent of theta is equal to O over A. This time we don't know theta, so theta will stay theta. Tangent of theta equals 66 over 50. This is something we've been doing on repeat for about the last week. How do I solve for theta?
Inverse.
Yeah, use the inverse tangent. Theta equals inverse tangent of that fraction, 66 over 50. Reminder, this is in the context of a triangle, not a triangle on a plane. So we're only going to use degrees, no degrees, minutes, seconds. That's for circles. So just type that in and we'll round to the whole number. Inverse tangent of 66 over 50. Again, make sure you're doing this in degrees in your calculator, not in radians. 52.8, so we'll call that 53 degrees.